conference.
Sure. I'll be sending.
Yeah.
So now I think we can start.
Okay. Good evening, all. So I'm going to briefly introduce us, that is IEEE AP-MTTS SBC IIT Kharagpur student chapter. So this is an endeavor of enthusiastic students from RF and microwave engineering background. Every year, this chapter organizes several distinguished lectures, workshops, small courses, and in-house lectures. Activities of the chapter are not just bound in the institute, instead they have reached many students across the country. And besides, this platform also encourages students to conduct various social activities and to be aware of the facilities and advantages a student gains as a member of the IEEE Antenna Propagation Society and IEEE Microwave Theory and Technique Society. It has also won several awards. As Best Chapter Award also it has won, and it has conducted site activity as well, funded by site, IEEE site. So today we are very pleased to have with us Dr. Chen, and Dr. Rinal Kanti Mondal will introduce her to us. So over to you, sir.
Thank you, Shreya. It's my privilege to introduce Professor Chen. Professor Ciciao Chen, a senior member of IEEE, received the BSc degree from the Beijing University of Posts and Telecommunications from Beijing, China in 2010, and the PhD degree from the Queen Mary University of London in 2014. In the same year, she joined the School of Electronic Engineering with the Beijing University of Posts and Telecommunications as a lecturer. She is currently an associate professor with the School of Electronic Engineering, Beijing University of Posts and Telecommunications. Her research interests include dielectric resonator antenna and mmWave antenna array. She was the recipient of the Best Paper Award in IEEE IWAT 2013 in Germany, third prize student paper competition in IEEE APS Urshi in 2013, Orlando, TICRA travel grant in UCAP in 14, and third place in QMUL 3-minute thesis competition in 2014 in UK. So with this brief introduction, let us welcome Dr. Chen, and I'm sure all of us will be beneficial from her expertise. So Dr. Chen, over to you. Thank you.
Okay, thank you, Professor Mandel, for your introduction, and thank you all for inviting me to do this seminar. I'm Zhijiao Chen from Beijing University of Post and Telecommunication, and this presentation is a low-cost mmWave antenna array for wireless future. And this presentation is on behalf of the IEEE APS Young Professional Ambassador, and I really appreciate to do this presentation in the Indian Institute of Technology, Kharagpur campus. And I know this university is very, very good and very distinguished all over the world. And especially in India, many good students are join here and have the chance to get an education. So I really appreciate to have this chance to communicate with you. So this is the outline of my presentation. And first of all, I would like to introduce IEEE APS Young Professional Ambassador Program. And you might have many seminars from this program. So I would like to tell you what you can benefit from this. And also I will introduce the consideration for wireless future and our recent work on mmWave antenna array, including a wideband, dual polar and dual polarization, multi-beam antenna, and so on. And finally is the conclusion and the future work. So maybe you, some of you already familiar with IEEE APS, and this is the APS is in the field of interest is include the antenna, and maybe some of you already study on the on antenna, and also the radiation and the propagation. Its application and system pertinent to the antenna propagation and the sensing are also included. And here is the scope of the APS. The number of the members is over 9,000, and there are 10 regions, and we are in the region 10, including the China and the Asia, Australia, and New Zealand. So it occupies around 32% of the all members. And here is IEEE APS at a glance. We have 9,000, more than 9,000 members, and over 200 chapters, including the chapter Karapur chapter is one of the chapter, and over 1,000 students, 500 IEEE fellow. And also the ecosystem of innovation supported by the 6 leading professional journals such as IEEE TAP, IEEE ADAL-PL, and the one flagship conference, which is IEEE AP-RC. And we also have the APS also has several awards, such as the awards for distinguished achievement in research and education, and also best paper award at travel grants. And most of these best paper awards and travel grants are for they are encourage students to join, so they are on the student only. So now I would like to share my experience of attending one of the IEEE conference, and Professor Menda also introduced that in your university there will be an antenna conference, and so this kind of conference always sets the best paper award. So at that time, it was my first time to join a conference, and I'm very lucky to have the best paper award. And here is the IEEE Life Fellow Professor Raj Mitra, who is very famous and very popular in Antenna Society, and he gave us a award. And in this conference, it held in the Karlsruhe, Germany, and the banquet was held in a castle. And in this castle, everyone was dressing like a king and or the soldier. And as the winner of the best paper award, we are on the stage and have the award from the Professor Mitra, and we dressing like this. And this guy is another best paper award winner, but because he's in the hammer, so no one can see his face in. And after this, we have these awards, and we have a ceremony like the Knight Declaration. And in this ceremony, the chair of this conference is acting like a king, and we are the soldiers for the knights. And he put a very long sword onto our shoulders, and saying that, okay, repeat with me. I will contribute to Antenna Society, and we repeat with that. And so that is quite interesting, and it was a very good, interesting journey to attend the IEEE conference. And here is another experience. I attending IEEE flagship conference, which is APS-RC in 2013. I was at that time I was a PhD student, and in this competition is very fierce, and the best the papers are selected from the best of the best of the best, and then there are 10 candidates, and after several rounds of competition, and with more than 10 judges, and I win the third prize. So I would like to share this experience with you, and because I would like you to pay more attention to the student competition in different conference. and especially the flagship one, because you can learn from others and also share show your best work to the antenna society and have the chance to get a word from the, for example, IEEE Lab Fellow, Professor Tenderbergs. Okay. So now I would like to introduce IEEE young professionals. Maybe some of you have already graduated from your PhD. So you can join the IEEE young professionals, which define as who has graduated from their first professional degree within past 15 years. So we include the graduate students, past doctoral fellows from academia and the industry. And you can learn more about APS in this website and young professional in this website. Also, here is the combination of the APS young professional. So in here you can know about the know about what's activity of the young professionals from all over the world, and you can also contact us on the LinkedIn. In here you can see the very latest work and the most popular work in antenna society. Okay, now we come to the ambassador, and before we give the presentation, we got trained on what is ambassador means. That means a person who acts as a representative or promoter of a specified activity. And as for me, I have my own mission, and I wish I could share my research experience with APS society and inspiring and encouraging more young people, especially young women, to join us. Actually, I'm not doing this work alone. We have a group, and our committee is a CJ Reddy, who is from the industry, and he always gives us a lot of courage on doing the presentation and share with us some slides to give introduction, and also Kama Abasi, who give us a lot of support. And here we are. In the first year of young professional program, there are 12 people selected. You can see we from all over the world, from China and the Europe and the USA, and also from India here. And I'm very pleased to say that to see that there are 4 ladies in here. So that means the number of ladies in the antenna society is growing. Okay, in respect to the young women engineer, I would like to introduce a movie named as Hidden Figure. And this movie gave me a lot of inspiration because the story is about 3 Black women who is under discrimination in America in 1960s. And at that time, their salary is only 1/10 of that of the male worker in NASA, but they never give up, even though they didn't, and the other male worker didn't respect them, but they working very hard and show their talents. And finally, they win the respect from the male workers. And actually, this is a true story. These 3 ladies are Catherine Johnson, Dorothy Wang, and Mary Jackson. And Catherine Johnson is very good at mathematics. And under his her hard working, the landing missions to the moon was successfully achieved. And the Dorothy Wang is the NACA's first Black supervisor, and also one of the NACA's few female supervisor. NACA is the previous name of the NASA, and this is Mary Jackson is work with Dorothy Wang, and she's a very good supervisor, and under her supervision, they use IBM first computer to achieve the landing missions to the moon. And in respect to this first IBM machine, its name is Corey 1, and located in the Los Alamos in 1970s. And at that time, the computer. This computer is very huge. You can see it occupies a whole room, but its computing limitation is very small, only 80 million flops. And the Thomas Watson, the president of IBM, says that I think there's a world market for maybe 5 computers. He predict that no one needs this computer, and so they don't think it will be a big market for the computer. But now you can see that everyone has computers. For example, iPhone 5, its computation compatibility is 7.6 flops, which is 1,000 times than the first IBM computer. And now the technology developing very fast. For example, in 2 years ago, Apple proposed M1, which has the compatibility of 2.6 teraflops, which is another 1,000 times than the iPhone 5. And in the very near future, we will the metaverse is coming. For example, the president of Facebook, Mark Zuckerberg, changed the name of his social network to Meta. His social company is becoming a metaverse company, and he also said that I believe the metaverse will be the successor to the mobile internet. That means it's coming very fast. And it's also very funny to know that McDonald's also get involved into the metaverse. They want to do some for example, virtual food delivery via this internet. And in this metaverse, people can go vacation, just stay at home, and you just connect to the internet, and you have a virtual identity, and you can go vacation, and you can enjoy the food, and also go shopping, such like that. It was a very, very cool word. So in this metaverse, our wireless future will be very aggressive. And I believe that the millimeter wave and terahertz is the only way to go higher, because we need to connect to the internet in anywhere and anytime, and also the bandwidth need to be very large to do the 3D imaging, and so that means the device need to connect to the base station point by point, and share the large bandwidth, and also is ubiquitous. That means the device is everywhere, and they need to connect to the internet with the low latency. So also in this case, we face many challenges in the antenna design. For example, we need to design the antenna with a high gain beam, and also the antenna need to be maximum because there's many users under this coverage, and also they are very expensive to fabricate. So in 2017, and I come up with a solution to figure it out. I would like to design the planar antenna array and in dual polarization with the SIW technology. So here is my very first antenna design. The name is a dual polarized wideband substrate integrated waveguide feed slow antenna array for 60 gigahertz. And for more detail, you can check this published paper. And actually, at that time, there are several millimeter wave slow antenna already proposed. For example, these designs, they achieve the array and in a very compact size. However, they suffer from narrow bandwidth. In overall, their bandwidth is smaller than 11%, and all of them operate in the single polarization. They do have some dual polarized millimeter wave antenna before 2017. They are very outstanding work, so I would like to present here. But they also have some shortcomings. For example, for this one, they suffer from the narrow bandwidth. Also, it needs 22 layers laminate to achieve the dual polarization. And for this one, because it has a very big feeding network, so the loss of the feeding network is very huge, and this result in the low gain. And for this one, utilize the liquid crystal to achieve the feeding network, but the efficiency is very low. So you can see it is very hard to achieve the dual polarization, high gain, wideband, and low profile at the same time. So in this design, in our proposed design, we use 3 layers of PCB to achieve the dual polarization operation. So it has the advantage of compact structure, dual polarization, wideband of 70%, and the high gain up to 22.2 dB. And the efficiency is more than 70%. And you can see from here, there are 3 layers, and this is the SIW. Maybe some of you already know that. It looks like the waveguide. However, it printed on the PCB by printing this grounded bias. And these 2 are the feeding network, and this one is the antenna. And this antenna, we use this subarray by using 2x2 antenna elements and the surrounding in a SIW cavity. So you can see these 4 antennas, they are surrounded by the grounded bias. And for this one, they work in the dual polarization, and this is the feed network for one polarization. This is another one. So the power is feed from here, and divide by 2, divide by 2, and divide by 2, and the feeding from these slots and the going upward to feed this antenna array. So I would like to introduce step by step how I designed this antenna and how to achieve the wideband and dual polarization at the same time. So this is 3 layers, and you can see this is the subarray with a 2x2, and this element and this subarray is fed by the aperture in here, and the power, that means the power from port 1 go inside and the resonant in this SIW cavity, and going upward and divide by 4 from this in this stage, in this cavity, and then feed these 4 antennas in the same amplitude and phase. And the same principle aside for the port 2, they go in here and penetrate from this upslope, this slope here, and going and the resonance in this cavity, and going up again and radiate. And so these 2 ports can be work in dual polarization with a very high oscillation, because these 2 modes are orthogonal with each other. And here you can see the oscillation is as high as 40 dB, and now we can also see that the antenna bandwidth is very large, because usually the slow antenna has this small bandwidth or narrow bandwidth, but for this one we cut a semicircle on the edge of the slope, like here. So in this way, the antenna bandwidth is enhanced. You can see without the semicircle cut, the bandwidth is very narrow, like here. And after we cut that and do the optimization on the radius of the semicircle, and the bandwidth can achieve around 70%. And here is the figure for the another polarization, and from by doing this, and we achieve the antenna with a very symmetrical radiation pattern with a low cross polarization. Okay, now we extend the 2x2 array to 4x4 array, like here, and because the 2 cavities are opposite with each other, if we feed them in the same length, it will come with the dual beams, because in the broad sides, the power will cancel from here and here will be canceled with each other, and result in the deep down. And so we in this way we assign an offset to this H junction here. This is the H junction, and then we doing the optimization to achieve the broadside gain, like here. And this come with the 4x4 array. With this, you can see both the both polarization feed network has an offset, and this result in the double layer feed network for the dual polarization, which is superior than the previous design I introduced before. And for this one, it used 22 layers of laminates to achieve the dual polarization, because they require these additional layers to give the offset on this S junction. And then we extend the 4x4 array to 8x8 array, and this is the result. And in this design, it comes up with a very similar problem, because the arms of different power dividers are not equal, so we call this unbalanced arms. And then we add some bias on one arm to make the balance with this output. And also we design a transition with a wideband to do the transformation from the waveguide to the SIW. And this give a very good result. And then finally, we do the fabrication on this 8x8 antenna array and measure it. And we can see there is a well agreement between the simulated and the measured result. And the wideband performance has been verified, also with a good radiation patterns, a very stable radiation pattern over the operation band. But there is a problem when I measured the gain. And at first, this antenna was measured, and but we found that the measured gain dropped, and it dropped around 5 dB. That means a lot. That means most of power going somewhere. It's not emitted and radiated. So at first we thought maybe it is a problem of the PCB layers. When they stack with each other, we use the screw. You can see the screws here, but maybe there's some gap between them that cannot be avoided. So at first we try to glue these layers together to avoid this gap. But however, this didn't come up with a good result. There is come up with another bigger problem because the shape of the radiation pattern is not directional anymore. It's become a flat top, and because at the beginning the measured gain dropped, but the radiation pattern is very good. So we think there must be something else a problem. Then someone suggests me to do the gilding. So we fix this antenna with this gilding equipment. You can see that the color change, and then we measure again in the same chamber with the same equipment. The measure gain come back, and the very approach to the simulated one. And here is the comparison of the simulated and the measured result. And you can see the measured results also has some problem with this fix. They have around 2 gigahertz downshift compared with the simulated one. Here is a simulated result, and here is the measured, and around 2 dB downshift. And so we do some simulation work to check what's the result. And here is what we found. We found the wire radius has a very huge impact on the radiation high gain band. For example, if we change the simulated wire radius to 1.0 millimeter, they have a very good agreement with the simulated one, like here. And the reason why the bias is smaller than expected is because you know, the previous one they do the gilding. I think the problem is because of the gilding. The gilding will make a smaller radius, and after that we also designed another antenna with 60 by 60 elements, and we found that we're very happy to find that the antenna efficiency is still higher than 70% with by scaling this antenna, because this antenna has a very simplified feeding network. So compared with the other antennas, we found that this antenna has low loss because they use the SIW feed network, and also reduce the number of layers compared with the previous one, the previous published work, and also the antenna bandwidth is enhanced and with a very high efficiency. For this antenna, in paper number 7, and they use the differential bonding waveguide to do the fabrication, which is a very high cost. And we only use the PCB to achieve the comparable efficiency with this one. So that means we make it low cost and have the enhanced result. So the features like depolarization, wideband, and the high gain, high efficiency, and in the compact structure with only 3 PCB layers. And we also do some investigation on novelties on the semicircle cuts on the slow antenna and the dual layer feed network for the depolarization. So we propose this antenna to synthesis depolarization beams in both sides. However, in our scenario proposing here, they must have several beams pointing to different users, and that means we need to extend to the multi-user MIMO, and we hope we can achieve in a very low cost. So I'm thinking about the scenario, how to achieve this wide coverage. We must go for the multi-beam. So what's the scenario? I'm thinking about in our wireless future, we can design a base station like the ceiling mounting one, and it will mapping a coverage with the high gain beams, and these beams are connected, are joined with each other to achieve the seamless coverage. So the next design is a dual polarized slow antenna array with a pattern diverse beams for massive MIMO. Actually, there are some multi-beam antennas in mmWave. For example, this one, and for these antennas, they inherit from some traditional method. For example, pattern matrix or the lens. So usually they have a very large feeding network because they design the same feeding network of the pattern matrix. So even though they achieve the multi-beam performance, their gains are degraded because their efficiencies drops very much. It drops a lot. For example, for these 4x4 elements with 4x4 beams, the efficiency is only 35 to 40%. So I was thinking about the reason why this kind of antenna cannot achieve the high efficiency and with a very huge size. And I was thinking because in our micro cell switch beam antenna, for example, this one, the feed network has a very similar size with the antenna array. So the antenna didn't look very much, very big, very huge, and also the loss in this transmission line is very low. However, if we extend to the multi-beam antenna in mmWave, the feed network in planar architecture will be very big, like this. For this antenna, the antenna is very small, just in this size, but their feed network is very long and very huge. And in this way, you cannot extend the number of beams as much as possible, because you need to consider the loss in the SIW structure. So this result some problem with the multi-beam feed network in millimeter wave. For example, large profile, high loss, and low efficiency. And this efficiency degrade with the beam member, and also result in the limited gain and poor isolation. So in my proposal, I think we can divide the feed network like this, just like separate the feed network, because it's is huge, and repeat the antenna array, because they are very compact. They cannot occupy so much space. And to make it more compact in low and the low cost, we can combine two of axis beam into one, and to result in the compact dual polarized antenna like this. And to make it a 2D multi-beam architecture, we can arrange this antenna in a circle, arrayed in a circle, and to do 2D multi-beam mapping like this. And in this way, it has several advantages, such as low loss and high efficiency, and the gain remains no matter how many multi-beam achieved. And in this way, we can try unlimited number of beam without sacrificing its efficiency. Also, it has the flexible arrangement, and each part you can measure individually, because for the traditional one, the whole structure need to measure at the same time. And if one element or component fail, and is ruin everything. But for this one, you can design it one by one and measure it. And if one disabled, and you can just choose another one. And also it has the high isolation between the beams, and very easy to extend to the maximum. So the problem is, how can we design this dual polarized antenna array with off-axis beams? So we can come up with the previous design, and I do a very simple trick to offset is a feeding slope to one side. In this way, this opposite slopes have the phase difference with a 90-degree, or in this when the offset to y-axis, or 40-degree for edge polarization. So this result in the vertical polarization with tilted beam to 23-degree, and the edge horizontal polarization has an offset of 10-degree. And by combining these two, and we can achieve these dual polarization antennas, and in one scope. And here we extend this 2x2 to this 4x4 it's 2x4 element, and you can see the antenna spin direction is fixed and very stable over the operation frequency. And also this two polarization has very high isolation, as much as 25 dB. And also the wideband performance of this design is maintained. And then we extend this 2x4 array to the 8x8 array. And we also fix the feeding network, and to make it increase or decrease gradually. For example, for the vertical polarization, the phase increase is 180-degree, and for the horizontal polarization, the phase increase is 90-degree, and then we achieve this high gain beam in dual polarization and pointed to different directions. And here, okay, this is the antenna prototype. Sorry, I think there is a marking here. So can someone do me a favor to remove them? Okay, here is the comparison between the simulated and the measured results, and we can see good agreements between them, and also the high isolation between the two polarization is observed. And when this beam pointing to different direction, they have a very stable antenna gain. And for this, for the measurements, there is a good agreements and with a very small cross polarization. And to achieve the maximum MIMO function, I combine one broadside antenna and the 8 beam tilted array and achieve this architecture. And in this architecture, we can do the mapping. In here, you can imagine that this is the multi-ceiling antenna and this is the ground. You do the mapping, and in here we can see there's a seamless coverage in this area, and in this area, the very stable gain over the operating frequency, and also for each plane, for example, this plane, the radiation pattern is stable over the 57 gigahertz to 64 gigahertz. And for all these beams, the isolation is very high because they didn't share the same network. These beams are separate with each other. And for dual polarization components, the isolation is more than 40 dB. And for the others, that's with a separate feeding network, the isolation is more than 60 dB. So this antenna is features like low loss and high efficiency and high gain, even though the number of beams are extended unlimited, and also flexible arrangement, and each part of antenna can be measured individually. So it's very convenient to extend to the maximum MIMO. So we publish in IEEE TVT, and the application is amended aerial vertical. The scenario is proposed like this, and it could because it's very thin, only 3 millimeters, so it's very flexible to install to the in this scenario. And in here, because we use a pattern diversity antenna, the whole size is very compact. And with these two designs, we are thinking about to see what the futures, our futures like. So I'm looking for this World Radio Communication Conference in 2019. They proposed the IMT and the 5G FSSS band, which has a very large bandwidth that covers from 24 to 43 gigahertz. That means almost 2 to 1 bandwidth. And also within this band, there are 50% are designed for the satellite. That means the CP antenna is required. So that's why our next step is go for circular polarization. You not only avoid the polarization mismatch, but also need to cover 50% axial ratio radiation bandwidth. So is it possible to do that? So here is our next design, and I will introduce how I come up with the idea and how we design it step by step. And this design actually is optimized by my postgraduate student, Dr. Tian. Sorry, it's Mr. Tian. He's not a PhD student, but the master student. Okay, so I was inspired from a very old article on curved antenna proposed by Professor Nakano. And in his first design, he believed that this antenna could has a very wide band because this is a non-resonance antenna. It's a traveling wave antenna. It's like the curved antenna it called this curve antenna, but it looks like the spiral antenna, but it doesn't have so many curves or so many turns. So it only has one turns. And then for the first version, its antenna gain is 8.5 dB with only 6.7% of 3 dB aspect ratio. But for the next one, this antenna is improved. The architecture is printed on the PCB. It also has a narrow bandwidth, but in this article, he mentioned that the overall optimization of the configuration parameter lead to a frequency bandwidth of optimized meekly 50% for 3 dB aspect ratio radiation. So that means he didn't achieve that, but he believed that this architecture can achieve 50% aspect ratio bandwidth from his calculation. And he published in IEEE IWAT in 2011 about it. And at that time, only when I was come up with this idea or inspire see this paper, there's someone also designed the curved antenna in millimeter wave with 30%. But I would like to push the limits on this design to see if it is possible to achieve a 50%. And here we are. And here is the final design. And we designed this antenna and with a 3 PCB layers. And this design fitting with the microstrip line and the divide power divide in this layer, and make a small curve in this layer and go to top and design on this curve. And it achieved it avoid the polarization mismatch by have a very good CP performance, and it is very compact. And it should mention that this fitting network has over 100% impedance bandwidth. In overall, it achieved a 2-to-1 impedance and 50% AR, the aspect ratio bandwidth. And in this bandwidth, it achieved very stable radiation pattern. So it satisfies the requirements by this WRC19. So here is our design. This is the antenna elements, and we optimize the current elements by designing a staircase structure. So the feed line is going from here and going upstairs by using the metallic bias, and the curve in here and going upstairs, and here's another curve. So for these structures, you can see its impedance bandwidth is very wide, and also has a very wide aspect ratio bandwidth. But its radiation pattern is not very stable. You can see it increase with the frequency, but it has a good bandwidth. So this unstable thing we will fix later by constructing the array. And for this element, it has a very good front to back ratio. You can see that there's a deep none on this back, and also small cross polarization and a stable radiation pattern over the bandwidth. And here is a design procedure. I didn't give them very present it in detail because you can find in the paper. And by utilize this working principle, we can do the optimization and do the calculation about this bandwidth. And here is the wideband design of the feeding network. The conventional has a narrow bandwidth, and we optimize this structure and then extend its bandwidth to more than 100%. And here is the input, and then here is full output, and the output is very stable, has a very stable performance, and that means the power dividing is in balance in the phase and the amplitude. And for this design, we do the fabrication and verify its performance with more than 2:1 bandwidth and more than 50% of Archer ratio bandwidth. However, we found a problem because we utilize the microstrip transmission line. We simulate the insertion loss of this feeding network because the measure at that time the measured radiation gain is not so good. You can see it has 8x8 elements, but the peak gain is 21.7. And the previous one, the first one I introduced, the same 8x8 elements, but it achieved a 22 dB. So we found that there is a high insertion loss in this feeding network because it is a microstrip line. So you suffer from the high loss in the millimeter wave. And this insertion loss is more than 3 dB. That means a lot. 3 dB means the power just cut to the half directly by using this kind of transmission line. So we compare with others, even though it has a very wide bandwidth, you can see compared with other TAP papers, it achieved the widest. However, it has the limitation on the high loss on the metal antenna and the feeding network. We didn't calculate the loss on the metal antenna, but the feeding network is very huge. So our next step, I was thinking about how to improve the efficiency. So this come up with my PhD work, which is related to the dielectric resonator antenna. If you're interested, you can see the papers when I win the best paper. And so we try to have a very high efficiency. And but for this antenna, it has some problem. It cannot directly design on the millimeter wave because if usually the DRA has a narrow band, and if we want to achieve the wide bandwidth, in the most excitation is essential. Also, how to because if we move to the millimeter, it will result in a small dimension. So in this way, we propose a millimeter wave dielectric resonator antenna array with enlarged DRA dimension and the wideband compatibility and high gain performance. And I also inspired by the very old paper published in 1983, proposed by Professor Long. And in his very first DRA paper, he proposed that this kind of antenna can be applied for the millimeter wave frequency region for avoiding the low efficiency of the millimeter wave antenna. So my idea is try to design a similar architecture in millimeter wave. So in this way, I designed the antenna with the back of the SIW cavity to extend its dimension, and also have a stake structure to extend its bandwidth. So in this way, it excite with the multiple modes and the wide bandwidth, large dimension, and the high efficiency. So the fundamental how I scale the enlarge the DRA dimension is like here. Just for example, this 2x2 cavity is 2x2 slots are surrounded by the SIW cavity, and this cavity have a very certain modes which can generate act like the high pass filter. By mounting over this high pass filter, this antenna has an equivalent to a smaller dimension, so we can enlarge its length from 0.22 lambda to 0.4 lambda, and in this way, and this antenna can extend to a larger scale. And by designing a stake DRA like here, and another modes of TE112 are excited, so this can achieve a wider bandwidth And with this design, we can see without the loading of these two DRA, and you only achieve a very narrow band. And with the loading of stack DRA and the wide band high gain are achieved. And also this antenna has a higher gain with a narrow beam width with small cross polarization. And here is the fabricated result. And this is the prototype. And to locate or align the DRA, and we use this template like here. And the measure results has some problem, because we believe that maybe the position or the fabrication of this 3D configuration is not very accurate. So there's a few dB drops from this from his simulated result. And for this one, we compare with the others, we found that our DRA dimension is much larger than the others, and also achieve the high gain and the wide bandwidth at the same times. And for our next step, I was thinking about we can use some 3D printing to further reduce the cost of the antenna. And in this way, I would like to inspire our undergraduate students to get involved in this research. So here is the antenna he is working on, and it is a circular polarized 3D printing dielectric loaded antenna using the inset waveguide to dielectric transition. And actually, he did a very good job, and also published a conference paper and win the best paper award. And for this antenna, the 3D printing is utilized because it is very low cost. And in the antenna society, many people has already tried the 3D printed antenna by designing this kind of home antenna with a higher gain or lower side lobe, or try different material to print in one antenna. For example, this antenna are printed by the metal and the dielectric. So I was thinking about design a home antenna with a complementary structure like this. And here is the slopes the slopes cut on the waveguide to achieve the antipodal slope antenna, home antenna. And by using the metal 3D printing, and the structure is like this. And we can design a complementary structure with the dielectric. That means with a dielectric material, loaded material like this. And so for this antenna, you can design transition like here that can be inserted into the WR34 without the flange. So in this way, the flange is voided and achieve the 43% of volume reduction. And by using the dielectric, we found more resonance, more modes are resonated in the operation band. And this results in, we can observe these modes in here. And from this calculation, we found that the dielectric, for example, they have the epsilon is higher, so that means more modes are resonated, such as TE21 and the TM21. So for the metal one, it only has two modes, which are orthogonal with each other to generate the CPU operation. But for this one, it has additional modes that maybe degenerate with each other or orthogonal with each other. So this result in the degree with a smaller cross polarization compared with the metal one, and also the beam width is narrower than the metal one. And also by weighting both designs, we found a 90% of reduction on weight are achieved. However, with this measure is a oscillation result, and we found that dielectric antenna is not very stable. So they only match in these 2 points, and for the others, the Ashoc ratio goes up, and so the Ashoc ratio narrowed down. And this come up with a conclusion that the dielectric loaded antenna may have a smaller dimension and lighter weight than the metal antenna, but it suffer from the higher fabrication errors, like here. Okay, this here is the conclusion of this report, and we design several antennas, and step by step. Usually we design one antenna and to solve the problem, and after that we found another problem and solve this new problem and found another one. And we also inspired by the old papers or some other professors, and also would like to inspire more young students to join this research. And in our future work, we found many opportunities for the low-cost millimeter wave communication. For example, we are designing some surface wave over the power line and try to come up with a very cutting-edge idea about the millimeter wave transmission. And we are also designing some body-centric communications for internet over things. For example, the nail antenna, the diamond ring antenna, and the teeth antenna. And we are also investigate on the new material that could be very low cost and very low loss to design the antenna. And we are keeping thinking about the observed ideas and inspire more young students based on our international research lab between the BUPT and the Queen Mary University of London. We are keeping doing so, and we believe that if at first the idea is not observed and there is no hope for it. Okay, this is the end of my presentation, and thank you very much.
Yeah, thank you, Dr. Chen. So now we'll have a short question and answer session. So already we have few questions. So Dr. Chen, can you see it or should I read it for you?
Yes, I can see the attendance.
Please take a few minutes, a few of them.
Okay. Okay, I can see the question. So let me repeat. The Brennan says, hi, by using waveguide with laminates as a dielectric in distribution network, the problem of loss in feed network or power dividing network will not be solved. So theoretically, the loss will be same as the microstrip transmission line because the majority loss belongs to a dielectric loss, which is same in two states. Oh, actually, I'm thinking about this problem because for this design, the loss is too high, and I was thinking about the reason, and I found that the loss including the radiation loss and the metal loss and the conducting loss. And for example, the SIW structure, they don't have the radiation loss and the conducting loss because it acts like the waveguide. And for this one, let me show you. So when we simulate this waveguide in the HFSS, it looks like radiating rather than going through. So we evaluate this the loss by setting the conductive loss and also the radiating loss. And based on a very old paper, we found a very old paper and investigate how much loss in 60 gigahertz, and they found it that huge. And we investigate in this on this 30 dB, and we found it's still very large. It's higher than the SIW. So we believe that the radiating loss and the conductive loss are also very important, especially in the millimeter wave. So actually, they are not the same. And you can see in this figure, we come up with this line, and it's higher than the waveguide in waveguide you cannot imagine that it has almost a 6 dB loss because in the simulation, for example, this SIW cavity, the power is a resonance within this cavity. There's a very small amount of power is leaking out, and this cavity is still.
Thank you, Dr. Chen. So maybe I can add just a few words to Bena. Okay. Obviously, when we load it with the dielectric, we'll have dielectric loss, but it won't be equal like a microstrip line. So in fact, you can consider, let's say, two coaxial cables of 50 ohm, but of different diameter. So thicker cable, it will provide you lower loss. So you can think of in terms of the conductor loss and dielectric loss. The moment you have higher electric field intensity, you face higher dielectric loss. The moment you have more surface tangential magnetic field, so N cross H, then surface current will be high. So think in that way. So obviously it will have higher loss, but not like microstrip line. Still, she is showing some improvement. So maybe we can then go to next question, slide number 20.
Okay, I think next question. Slide 20, adding bias is trial and error method or any techniques. Let me turn to 20. You mean this bias, right? I think it's this bias. Actually, it's like a trial and error. In my understanding, I think the bias means this offset, and actually we can calculate the length regarding to its phase change. But in here we use the trial and error method. And okay, the next one. When the device connected to the base station is moving, then the beam should also change its direction to remain connected. How this beam steering compatibility in case multi-beam antenna is achieved, and what is the amount of complexity involved? Okay, this is a good question. Actually, this is the signal processing problem. Oh, sorry, this and I understand that for example, for the base station, there are two methods. One is adaptive beams. That means the beam is tracing the user, but they also need to update very quickly by using the Shin beam synthesis or the algorithm behind. You can understand. You can think of the algorithm behind. But for the switch one, it is also very common for the base station antenna because for example, this antenna, this device moving from here to here, and then another beam is pointing to this. They doing the handover method, which is will be investigated by the network layer rather than the antenna layer. So they will switch very quick, and they have the hard switch or the soft switch, and during the switch, and this mobile is still connecting to the mobile base station, and the multi-beam antenna, multi-beam or the switch beam method is also very common method for the base station. Okay, is that and what is amount of complexity involved? Actually, both methods are complicated, but I think the switch beam method is cheaper because adaptive one you need to chase it, and so the algorithm is updating like every second. So if, for example, if you are taking a train and it's going very fast, sometimes your signal will be very low. And for the switch one, because they just switch from one beam to another, so that's more easier rather than doing a lot of calculation for the Shin beam synthesis. Okay, this is my understanding of your question. Okay.
It seems that we don't have any more questions. So
Okay,
let
thank
me
you.
thank you. Yeah, thank you, Dr. Chen. Thank you for your time and sharing this useful information. I'm sure that the whole community will be benefited from this. And I would also thank all the attendees. Now over to the organizer. Shreya, please.
Okay,
Thank you,
so
Mondal
much.
sir. Yeah, thank you, Professor Chen. Mondal sir is also Vice Chair of IEEE Kharagpur section, and he found his valuable time to spend here. And it was a great talk from you, Dr. Chen. Thank you. Thank you for such
Thank you.
a nice talk. Thank you.
Okay, I will also like to thank you for attendance and also invite me for this presentation. And I hope we can keep in touch. And here is my email address. And if you have any question or comments for this presentation, you can send me. And thank you again for coming.
Thank you, Professor.
Thank you. Okay, thank you. I'm leaving this meeting room. Let's keep in touch and take care. Goodbye.
Thank you.
Yes, ma'am. Thank you.
Thank you, ma'am.